This is problem 129 in your textbook, and this is a nice example of a problem where Smith and Van Ness gives you a end of chapter problem that seemingly has nothing to do with the material that's in the chapter. So you'll probably see this a couple times, and but I want to go over this problem because it shows you some numerical methods that you probably haven't been exposed to yet, but you will be exposed to later on in the future. This problem is known as a nonlinear regression problem. And so I don't know if you have dealt with linear regression in the past. Linear regression is, as the name implies, it's where you're dealing with straight lines. And so if you've got linear regression, you've got y equals mx plus b, right? And so you are given a whole bunch of data points, and then what you want to do is you want to find the equation of a line that fits those data points. And so the way we can do this is your calculator can do it for you. Excel has automated routines that do this for you. You can do this in MathCAD. Just about, you can do it in MATLAB, you can do it in Python, you can do it in just about anything. If I have a case like this, what I end up having is my values of y, my values of x, and say these are my experimental values. And then what I want to do is I want to have a predicted value. So I set up a predicted value, and this is going to be my predicted y. And so the way that you can do this in Excel is my slope and my intercept, m and b, will have certain values. So I could put 1 and I could put 2 here. All right. And then what I would do is I'd have my experimental values for y and x, and then I would plug my model, which is y equals mx plus b. I would use these guesses, these initial guesses, to get a predicted value. And then what I would do is I would calculate a difference, and then a difference squared. And then I would sum up those square differences, and I would try to minimize that. I would try to find values of m and b that minimize the square of that. That is called least squares or linear regression. If you didn't follow that very closely, going through that pretty quickly, there's a lot of tutorials online. Hopefully, I'll go through this example a little bit more slowly and methodically, and hopefully you'll be able to figure out what's going on. So anyway, in this problem, you're given some pressure and temperature data. So some vapor pressure and temperature data. And you are asked to make it fit an equation. It's a nonlinear equation called the Antoine equation. And this is something that we'll be using later on in I believe in chapter 3. So anyway, the key to doing good Excel spreadsheets is to be organized. And so I've got everything already in place here so that I don't have to spend a lot of time typing. But I've got my experimental data. And so they give you the experimental degrees in the experimental temperature in degrees Celsius. And so I've entered that. And notice in the Antoine equation that they give you on page 23, we have to have the temperature in degrees Kelvin. And so all I've done is I've taken the temperature in Celsius and added 273.15 to get Kelvin. And if you haven't used Excel, so I can take this equals cell B6 plus 273.15. That's my answer there. I can copy and paste it down, but if I'm a real Excel jock, I can just know that I can double click and it will fill in down to the end of the line. All right, so now I have my temperature in Kelvin. Notice they give us also the pressure in kilopascals. And one of the things you should notice is that in the equation, they have log of Psat divided by kilopascals. Why do they have divided by kilopascals? The answer is because you cannot take the logarithm of a kilopascal. You cannot take the logarithm of any unit. All arguments in this class and in any other class that you're taking, when you are doing exponentials or sines or cosines, well, those have to be radians. So I should say exponentials or logarithms especially is what you'll run into. The arguments within the parentheses for those operators, for the logarithm or the exponential operator, those arguments have to be dimensionless. If they have dimensions in them, you're going to get the wrong answer. So that's what we're dealing with here. So we've got the pressure in kilopascals, and we need to convert that to log of Psat to fit the Antoine equation. So that's what I've done here. And again, the natural log in Excel is just ln parentheses E6, and then I can just copy and paste for the rest of that. So what I have here, these columns here are my experimental data. Now, what I want to do is I want to figure out what's the predicted value of, now what I'm doing here is I'm setting up my linear regression, my least squares, or I shouldn't say linear regression. This is going to be a nonlinear regression because it's a nonlinear equation, but I'm setting up my least squares fitting of these data. So if I look at my equation for the Antoine equation, I've got three constants. I've got A, B, and C. And so what I'm going to do, so what I have here, and again, remember, formatting is a big part. I could put this anywhere, but I'm putting it on top here. I've got my A, B, and C cells just as labels. These are just labels. And then these are the values. Now, I've been playing around with this, and so I've got some values that are going to work really well. But let's say I had no idea what the values were of A, B, and C were going to be. So I'm just going to put 1, 1, and 1. All right. Now, so these are my initial guesses. Now what I'm going to do is I'm going to calculate log of Psat based on my initial guess here. And so that's what this column is. This is my predicted log of Psat. And so if you look here, this is my formula. And so let me just type this in here. So this is equal to A. And so if I want to fix that, I type F4 when I do that, or I could type these dollar signs individually. That's fine. All right. Minus. Now in Excel, I'm going to use parentheses. So then I'm going to have B, F4 fixes that reference so that it doesn't move as I copy and paste. Divided by now temperature. What is temperature? I have to use the Kelvin. So that's going to be C7 plus now my C parameter, F4. And then I'm going to close parentheses on the bottom and then close parentheses overall. And that should be my value. All right. And so let's see if I copy and paste this, I should get the same number. I get the same number. All right, so I didn't make any mistakes. So I can just, if I want to, I can also drag this down and it will copy and paste. Or again, I could just double click. Once you see the little square on the corner, I can just double click and it will fill down to the end of the column. So this is my predicted value of Psat given the temperature and these parameters in the Antoine equation, right? And notice that this is a really bad prediction, right? This is a really bad prediction. If I look at the log of Psat versus the actual measured experimental log of Psat, you see, well, I mean, it's not that bad. It's kind of close there, but boy, it gets to be a big difference as we go through. Right? And I've already set up the graphs. You can work by yourself on setting up how to set up Excel graphs, and you can see that the The experimental are always data points, and the predicted are you don't want the predictions to look like data, so we make those just solid lines. That's one of the things I want you to make sure that you do as you go through your chemical engineering career. Don't make your predicted model values look like data points. So your actual data should be discrete data points, and your model prediction should be a solid line that hopefully will fit the data. And of course, we have a really bad fit, so that's why we see this here. So what do we want to do now? Well, we want to do least squares. We want to minimize the sum of squares of differences. And so what does that mean? Well, the first thing is the sum of we want to calculate the square of the difference at each of these data points. And so that's what this column is that I've labeled as difference squared. And so I want to take the predicted value minus the experimental value and square it. And so that's what I have here. So this is equal to, and I'm going to use parentheses, H6 minus F6, and then square it. All right. And you see that's a pretty small difference. And then I just copy and paste that down. And you can see as we progress here, our difference square gets even bigger. Now, in regression, in least squares fitting, what we want to do, we don't want to minimize each one of these. We want to minimize the sum of all these. So all I've done here is I've taken the sum of this entire column. And so as you can see, to do a sum, you just select, close parentheses. That's the sum of squares of differences. I just wrote sum of squares. All right. So that's setting up, I have my experimental data. I have a predicted value for my function that's based on my initial guesses. These are horrible guesses, but that's what I'm going to start with. And then I've calculated the difference squared at each of these points and then sum them up. Now is when I can use the Excel solver. And so to get the Excel solver, if you don't have the Excel solver, if you see here, I've got my data clicked here and I see solver over here. If you don't have that, go online, all the Google, there's a whole bunch of places that will tell you how to get it. You go here and you go to add-ins and you can manage the Excel add-ins and you can add the solver. And so you can see here I have the solver add-in. I also have the analysis pack VBA. I do a little bit of VBA program and also the analysis tool pack. This analysis tool pack has the built-in linear regression that I use a lot as well. So go to Excel, put all these add-ins in there. I would definitely recommend that you do that. You can see there's a number of other add-ins that you can add, but we don't need those right now. All right, so let's see how the solver works. So I click on the solver, and I've got some things. This is already entered because I've been playing around with this. But what do I want to do? So for least squares regression, I want to minimize the sum of squares. And so that's my objective. My objective is to minimize the sum of squares, and it's going to do that by adjusting my A, B, and C parameters. And so that's how I set it up. What's my objective? My objective is in this cell right here, my sum of squares. So I click on that. So I-17. I want to minimize. I don't want to maximize. I don't want to set it to be a value of 0 because probably this is not going to be an exact fit where I will get a 0. And so if I set a value of 0, it's probably never going to converge. And so what I do is I want to minimize it. So that's going to minimize it. And how am I going to minimize it? I'm going to do it by changing these variable cells. Well, what are my variable cells that are going to be changing? It's not any of the data or anything here. It's these parameters, A, B, and C. And so I'm going to select these 3 cells. So those are my cells. Do I have any other constraints? I don't really have any constraints that I really need to add. If I wanted to add constraints, you can see you can do this, and you can go on to 20 different YouTube channels, and you could find how constraints could be added. I could say I could limit A, for example, to be less than 5,000 or something like that, or whatever you want. But we're not going to have any constraints here. All right. Do I want to make unconstrained variables non-negative? I'm going to leave that unchecked. And then solving method. I'm not simplex. This is a linear equation solver. I'm not going to use this. GRG nonlinear. This looks for, I believe, this looks for local solutions. If you go into the text, and this is a little beyond what we need to worry about, but when you get into your chemie computation courses and linear programming and things like that, you're going to learn that there are functions out there that can have many different solutions depending on what you're looking for, and you can have local solutions or you could have global solutions. So you can think of a function that has local minima or a global minimum, and the GRG nonlinear is going to search for local solutions. We'll talk a little bit about that. The evolutionary, this searches for an overall solution, a global solution, and we aren't going to do that. So we're going to stick with this. There are options here. You can set the constraints and things like that. I'm not going to worry about those right now. But this is how we set up the solver. Our objective, we want to minimize the sum of squares. So we click on that sum cell, and we click on minimum, and we want to do that by changing these three A, B, and C values. Once we have that, then we hit solve. Hit the solve button. Whoops. I accidentally changed that. So make sure that's right. Okay. So now we can hit solve. And you come up with this little sheet here. Do we want to keep the solver solution? Yeah, I want to keep it. I don't want to restore it because then I'm going to lose my answers. I'm not going to deal with the reports or anything like that, and I don't need to go back to the solver parameters dialog. Let's look at what our solution looks like. So let's just click OK. So solver has converged to the current solution. All constraints are satisfied. Notice it performed 5 iterations for which the objective did not move significantly. If we want to get even better, we can try a smaller convergence setting or a different starting point. But let's see what we have here. So let's look at the values of A, B, and C. The values of A, B, and C, 15.38, 33.14, and then minus 21.27. Let's look at the predicted values. Here are the newly calculated predicted values of log of Psat. If I look at them, they look a lot closer than what we had before. If I look at my different squares, differences squared, you can see that now I've got really small numbers here. And my sum of squares is a pretty small number. Then I look at my predicted pressure in kilopascals. 3.25, 3.18, 5.5, 5.48, 9.3, 9.45. There are differences, right? There are differences, and I've calculated the percent difference from the experimental, and you can see that overall this percent difference looks pretty good. I mean, this is probably well within the experimental error of the measurements that were done. Now, we don't have replicates measurements at each data point, so we don't have error bars, which if you were doing this in a lab, you would definitely want to have replicate measurements at each temperature so that you have error bars and so forth. But here we just have one data point, and you can see that the largest error we have is about 3%. Usually experimental error for good precision measurements, you would hope to have at least less than 5% relative errors. And so we've definitely done that. Then if you look at the graphs, this is a graph of log of Psat versus temperature in Kelvin. You can see that our data points are orange and our experimental fit is the blue line. That's a pretty good fit, right? If you look at the graph of Psat versus temperature, now our data points are the red markers, and again our fit is the blue line. You can see that that's a pretty good fit. All right, and if you do an average, and so this is taking into account both positive and negatives, so we're looking at the average percent difference, we got about 0.005%. That's pretty small. So this is a nonlinear regression that's done in Excel. One of the things I was doing is I was looking at the answers in the textbook that they give. The answers in the textbook are different. Let me just type them out. They claim that they did this same thing in Excel and they got 12.74 for A. They got 2017.87 for B. And they got minus 80.87 for the C parameter. Why is that? Why would they do that? Did they do it wrong? Maybe they were using maybe they were using Excel 2013 or who knows. No, they didn't do it wrong. This is just a different answer. This is not a problem. This kind of a problem is not one where you have one single absolute right answer, because what we are doing is we are providing the solver a starting point. Remember, what did we type in? We typed in what, 111 or something like that, right? And what the solver did was it took that, put that in, and then it started adjusting using the search algorithm that Excel has built into this, and it came up with these parameters. And notice they said after 5 consecutive iterations, the sum of squares did not change very much. So it just didn't change very much. If you look at the value in the textbook, they list in the solutions, they list a sum of squares error of 5.01 e minus 03. So 5.1 times 10 to the minus 5.01 times 10 to the minus 3. They actually had a larger sum of squares than we did. All right. So we actually let you could argue that our answer, you could try to argue, and maybe you might be right, our answer is more right than their answer because we have a lower residual value, sum of squares residuals, than what they did. So maybe they had their constraints, their iteration parameters were a little less or a little more lax. They didn't require the convergence to be quite as tight as what we had. So, you know, this just illustrates the fact that for these kinds of problems, you can have more than one solution, and it really depends on how tight you want to set your constraints. So that is in, you know, if we wanted to, we could paste these in here. So let's put those in. All right. And let's do the solver with these values. And so notice that the solver then came to 14, 2600, 51 minus 51. We got an even smaller sum of squares than we had before. Remember, we had, I forget, was it 2 times 10 to the minus 3? Now we got 5 times 10 to the minus 4. So maybe we're even better. If you look here, our max percent difference, remember it was around 2 or 3%, right? Now it's 1.5%, right? And our overall average percent difference is even smaller. So what you can see here is by having better and better guesses, we can get an even better fit and even tighter numbers on our parameters. So, you know, for this, if I were to give you a problem like this, I would just say make sure that you're at least aware of what your convergence is, what your sum of squares is going to be. You know, if I were seeing 5%, if I were seeing 5% differences here, and I knew that I should be getting a little bit better, then I would do a little bit more guessing and do a couple iterations on these guesses for the A, B, and C parameters and see if I could tighten that up. But for the sake of what we're doing here, this is fine. So this is nonlinear regression using the solver function in Excel. The solver function is a powerful function in Excel. We will probably use this in chapter 3 when we start talking about solving cubic equations of state for volumes, and so it would be good for you to kind of get used to using it here. We'll go over this again as we set up our equations of state calculations. I also had some questions from some students about using MathCAD. And MathCAD can do a lot of things, but nonlinear regression is not one of the things MathCAD does very well. At least the MathCAD 2000, and from what I have heard in working with students, MathCAD 15 isn't that much better. MathCAD does have some nonlinear regression functions, and if you really want to use them, I'm sure you can. If I was looking through my manual, they have some specialized regressions for some common equations that one finds, for example, in electrical engineering and things like that. They've got EXP fit, LGS fit, log fit, power fit, sine fit, and I think those are primarily from electrical engineering calculations. They have a generalized regression. So they've got linfit, L-I-N-F-I-T. So if you want to type that in to help, you can get some information of that. But that is for linear. That's a linear combinations of the function f that best approximates the data. That's kind of a you can do that, but this problem doesn't lend itself to it. They've also got genfit. Genfit is a function that returns parameters for the best fit by the possibly nonlinear function defined by f to the data points in the vectors x and y. So you've got your x and y data. F is a function that returns n+1 element vector containing f and its partial derivatives with respect to each of its n parameters. What that means is you are going to, if you were to do this, you would have to take this Antoine equation, you would have to start calculating some partial derivatives and things like that. And as soon as I read that, I was just like, nah, I'm not spending time doing that, dealing with taking partial derivatives of something like that, just to do something where I know that in Excel I can set up a solver equation and do it a lot more efficiently. So that's maybe just a little lesson there that, you know, I have hyped up MathCAD pretty good here, and I do think it's very useful for lots of engineering calculations, and I would still encourage you to use it quite a bit for your quizzes and your exams. But realize that MathCAD and really any programming tool or language is not going to be perfect for everything. The one thing that I'm liking about Excel is that it is becoming more and more powerful. And when you get into your lab courses as juniors, your chemical engineering, your first chemical engineering lab course, and especially your senior chemical engineering lab course, you are going to have to be proficient in Excel. And so I would encourage you to try to do as much and learn as much about Excel as you can. You know, maybe I'm weird, but in the evenings I kind of like watching Excel YouTube videos, tutorials on how to do certain things. And so I'm continually trying to learn how to use Excel, for example, to handle all the big data that I deal with in my research. As you can see in Excel, you have to keep track of the units yourself. Excel will not do anything for units and units conversions. You can also see that it will just fill in the significant digits as much as it can. You can, you can manage that. I like using scientific notation a lot of times. And another thing that you'll find, make sure that you're good at doing graphs in Excel. Again, it puts all these significant figures in here that you really don't need. So if you're going to make something for a presentation or publication, make sure you're going to have to spend the time to pretty things up. Like I said, with Excel, you end up spending a lot of time formatting things to make things look nice and look right. Also, remember, for every graph that you make, you need to have your axes labeled, and also with the units that you're going to be using. Also, make sure that you have an accurate and descriptive legend so that people can read the graphs. If you don't have those things, you will get lots of points taken off by me and Professor Flodman and whoever else is going to be giving you these kinds of things. But that is Excel with Solver, and like I said, we're going to be using this throughout the semester, so it would be useful for you to play around with it. There's a lot of examples on YouTube channels, and that you could try it, but maybe go ahead and try it first with this problem, and then we'll be ready for chapter 3.